All right, on Thursday we covered amino acid synthesis, and so far we've only covered racemic syntheses for amino acids. The first one was a variant of the Hell-Volhard-Zielinski reaction, where we brominate a carboxylic acid in the alpha position, then we can substitute it with an amine, and then we can purify it. So pretty straightforward for that one. The other variant we saw was the malonic ester variant, where you use diethyl acetamidomalonate. It's a mouthful. You deprotonate the alpha proton, alkylate it, and then hydrolyze everything apart in order to get to your amine. And now we have one last racemic synthesis I wanted to cover, and this is called the Strecker synthesis. All right, in the Strecker synthesis, the overall mechanism is pretty straightforward, and then we'll go through it step by step. You'll start with an aldehyde, and then you'll take ammonium chloride and sodium cyanide. Not the most friendly reaction in the world to run, reacting something with cyanide. But when you do this, your cyanide group can add in along with your amine, and you end up with a cyanohydrin derivative. The next step, we can take acid and what do acids do with cyano groups? So, yeah, we can change it to a carboxylic acid, right? So if we have a cyano group, you can convert that cyano group to a carboxylic acid. And if we look at this, it doesn't look like the standard way of drawing an amino acid, but it is an amino acid. So let's take a look at the mechanism. All right, first step. We're going to take our aldehyde, and we're going to react this with our acid. So ammonium chloride is a weak acid, right? We've got the ammonium cation in there. And so we can protonate our oxygen. Hey, you guys in the back, can we not have side conversations? It's distracting. And we can protonate that carbonyl. Now we've got a free ammonia molecule in solution. So this can add into our aldehyde, kick up electrons. And we get our ammonium here and our hydrogen down there. Now if we have more ammonia around, what will happen? Yeah, just deprotonate your amine. Oop, shoot. In the next step, we've got more acid around in solution, so I'm going to draw this as just H+. And we can protonate our alcohol. So this should look very familiar to you guys, right? Looks exactly like our imine formation. All right, so we've converted our aldehyde into our imine. These are all under equilibrium conditions. I'm just shorthanding it with single-headed arrows. The next thing we have is we've got cyanide around in solution. And the cyanide can attack in, kick up electrons. Oop. And we get to our final product. Now if we treat this with acid, I'm not going to show all of these steps because it's very steppy, but we can convert that cyano group to a carboxylic acid. So we've essentially added one carbon onto our chain, and we've got a protonated amine. It's still important to remember that with the Strecker synthesis that it's still racemic. If you do want to review this mechanism, I would recommend looking at section 2113 if you're unfamiliar with acid hydrolysis of nitrile groups. All right, so the one problem with doing all of these is you immediately lose 50% of your product because it's the wrong isomer, right? Yep.
So synthesis-wise, could you do anything to that product? Because, you know, it has an NH3 and also carboxylic acid. Could you do anything to it or not?
Yeah, we could do more chemistry on this. We still have alpha protons on there, and we can do reactions on the nitrogen position. We can do reactions at the carboxylic acid oxygen.
But you don't need, like, protecting groups or anything like that?
We're going to get into protecting groups, but yeah, it's very protecting group heavy anytime you work with amino acids. All right, so anytime you do these racemic syntheses, you lose 50% of your product. To be perfectly honest, nobody does these anymore. They're not applicable, they're kind of wasteful, and they take too much work. So instead, we've got a much, much better route. The easiest route, to be perfectly honest, is nowadays you can order any amino acid you want from a chemical vendor for very, very little money. But this route was kind of the lead-in to these manufacturers developing enantiopure amino acids. And so what they did was they had an acylated derivative of an amino acid that looked like this. So essentially the R is the side chain for your amino acid. And what they were looking to do was to do hydrogenation that was enantiopure. And so in order to do this, what they did was they took hydrogen gas, and then they had a chiral catalyst. And so by using a chiral catalyst, the hydrogen could only be delivered to one face of that alkene and not the other face, and they could develop a scheme that would only give you an enantiopure product. And then in the second step, we need to pop up that acyl group down here. So how can we remove an acyl group? Yeah, we need to use acid or base to hydrolyze our amide there. So in this case, I'll just choose base and water. And then in the last step, we want to protonate everything back to its true form, so we'll just do H3O+. And when you do this, you get a product with your correct amine, and oftentimes the percent EE is greater than 99%. Oh, let me erase this. Percent EE can be approximately 99% or higher. So you gain exclusive stereochemical control over your product. So the question is, what chiral catalyst is used? It looks pretty funky, so bear with me as I draw it out. And if you remember back to our hydrogenation section, it should look fairly familiar. So I'm going to shade these in. These aren't double bonds. And then we've got phosphorus atoms popping off on the inner side of those benzene rings. And then we've got phenyl groups here, here. So this is our ligand that we have. It's called a binap ligand. And they react this with a ruthenium catalyst, or sorry, ruthenium metal. And the ruthenium really likes to bond to phosphorus, so it will bond up like that. And then we also have 2 chlorines on there. So the formal name for this molecule is R. It rotates light in the positive direction, so we usually write plus. And then we write RU binap. That's for binaphthyl. Those 2 benzene rings that are fused together are called naphthyl groups. And then Cl2. This is the chiral catalyst that was developed by, I think it's Robert Knowles, and he won the Nobel Prize for doing enantioselective hydrogenation in, I believe, the 70s. The weird thing with this molecule is it doesn't look chiral at first glance, but these benzene rings actually can't stay in the same plane. They'll actually be cocked, and that's why I have the sides shaded in like that. And so what you end up with is something called axial chirality. And therefore, due to this chirality, it can only deliver H2 to one face of an alkene. And this completely revolutionized peptide chemistry because all of a sudden it wasn't a pain in the butt to make peptides. You can make these on large scale, and then ultimately chemists don't even make them anymore today. They just order them from a company like Sigma Aldrich, and they'll ship you a bottle in a day or 2 of the amino acid that you want. All right, so now let's go into synthesis of peptides. The idea of synthesizing peptides has been around as long as human beings have known about peptides. The problem is the logistics of doing it are not easy. So I'm going to come up with a list of problems. Problem number 1. All right, problem number 1 is if we take a carboxylic acid end of an amino acid and we tried to react this with the amine end of another amino acid, you just get proton transfer. You can't just throw these in together and expect them to couple, right? A lot of people are tempted to say, well, why don't we throw in some acid, protonate the carbonyl oxygen, and then have the amine add in? Problem is, if you protonate that, you're also going to protonate your amine, and your amine's going to be a crummy nucleophile. So there's really no shortcut around these problems. So the amine, if protonated under acidic conditions, is a poor nucleophile. And then other people will say, well, what about just forcing it and doing it under really, really basic conditions? But then you run into the problem of the alcohol, that OH on the carboxylic acid being a really poor leaving group, right? You're not going to expel an O2 negative. That just never happens. There is no leaving group. So what's maybe one strategy to get this nitrogen to add into the carbonyl? Yeah, we need to turn it into a better leaving group. That's exactly it. So a lot of people say, well, can we turn it into an acid chloride? Yeah, you can, but most people don't do it that way. So I'll show you the way most people do it. But Ian's exactly correct. We must turn the OH into a good leaving group. And so the way we use this is we actually use reagents that are specifically designed for peptides. They're called peptide coupling reagents. And I'm just going to show you one. This is the one your book shows, but in reality there are dozens of them that you can select from. It's not just a one-shot sort of deal. A very popular one is this one. It's got 2 cyclohexyl groups. And what this is called is dicyclohexyl carbodiamide. People get really tired of writing out this name, so people just write DCC. Much easier. And this was one of the earliest ones developed. There are actually better ones than this that are more commonly used, but this is kind of the tried and true one. It's been around for a long time. So let's see how this mechanism works if we use DCC in our reaction. All right, so if we've got a carboxylic acid, and I'm going to abbreviate the cyclohexane rings with CY, it can react with DCC. And we've got these nitrogens on there that are somewhat basic, so they can just grab that proton. Pretty simple proton transfer. We get a nitrogen here. Let's see why. All right, now we've got a carboxylate, which is at least a decent nucleophile. What can this carboxylate maybe do? Attack the carbon, right? So we've got a nitrogen with a positive charge. If we attack that carbon, we can kick up one of those pi bonds onto the nitrogen. So this can attack there, kick up electron density. We still have our cyclohexyl group. And there we go. All right, now we're set and ready to go. This is actually a good leaving group, and you'll see why here in a second. But I'll just circle it and say good leaving group. And so in the next step, we can have this react with our amine. So I'm going to try to color code things a bit. This amine can now do the attack on the carbonyl. I'm going to move this CY over there. All right, so our amine added in. What do you think we can do now? We've got to move some protons around probably, right?
Have the oxygen along the negative come down and then kick off the other one?
Not quite. First thing we need to do is we need to move a proton from the amine over to the nitrogen on the carbodiamide. So I'm going to write plus or minus H plus, just to indicate a proton transfer. Okay, so let me add in our amine. Okay, now we're ready to kick off our leaving group. So let's show the electron pushing. This can clamp down, this can clamp down, and this can clamp down. So it's a domino series. And now we've got our new peptide bond. So this bond is where that carboxylic acid used to be. And the other reagent is pretty handy, or the byproduct, I should say. Oop. It's a urea derivative, so we've got kind of an amide on both sides. We call those ureas. You can do a simple aqueous workup, so extract that away, and then you recover your pure amino acid. So you don't have to do column chromatography, which in a chemist's mind is one of the greatest things ever. Anytime you can simplify the reaction and purification, it makes your life a lot easier in the grand scheme of things. So this is how new peptides are how new peptide bonds are typically made. Is you react it with DCC, turns your carboxylic acid OH into a good leaving group, and then you can throw in an amine and get the peptide coupling to work. But there's another problem. So let's go to problem 2. Problem 2 is often overlooked. So let's say we react this amino acid. I'm going to just label it as the black amino acid. And we'll react this with a blue amino acid. And we decide, let's just toss these two together. We've got DCC. In our mind, we would think, yeah, these will just couple together, right? We've got a carboxylic acid, we've got an amine. The problem is we've got 2 carboxylic acids and we've got 2 amines. So gaining control of this reaction is non-trivial. So what you get is a huge mixture of products. So you do get some of the correct product. Oop. Sorry. However, you also get some of your amino acids dimerizing together. So you may also get, forgot my primes there. So you may also get 2 black amino acids coupled together. And you can actually get 2 more products. So if we look at this, what we could have are two black molecules coupled together, two of the blue amino acids coupled together. We could have blue and black coupled together, but it also matters which side is on what end. And so what we call this end is the N terminus. And we call this the C terminus. Oop. And if we have the blue end at the N terminus compared to the black end, it's a completely different peptide, right? So we're going to make a mixture of 4 different peptides. So what do you think a solution is if we want to selectively get that first one?
Just react with that instead of.
So let's say we did want this one right here. So we want to react the black one with the blue one. We want the black one to be at the N terminus, the blue one to be at the C terminus. That means we're going to have to do something about that blue OH group right here, right? We don't want this reacting, and we also don't want this reacting. So instead, what we're going to do is try to block those. So what we have are protecting groups for these. If we want to exclusively get the first product, these must be protected. Oh. And the reality is there are actual series of books just on protecting groups. I think I had one in my old lab that was like 900 pages long of just protecting groups for various positions. The book just cherry picks the most common one, and those are the ones I'm going to show you guys. But the reality is, I mean, you can pick one of 1,000 different protecting groups, and these reactions will work. Oftentimes, if you're doing natural product chemistry, you have to be very particular about your protecting groups. So let's first cover our nitrogen protecting groups. You guys have actually seen these without even knowing it. Do you guys remember seeing Bach on one of the problem of the days? And I think I told you guys Bach is just a protecting group, ignore it. Well, now we actually get to see Bach in action. And the question is, what does Bach stand for? Bach stands for tert butoxy. Tert butyl oxy carbonyl. It should be butyl, not butoxy.
I was just saying that this is what the Y now.
Oh, oh my gosh. Sure. I know, we're all getting tired, guys. All right, so that's where the Bach comes from, is the B, O, and C, and tert-butyl oxycarbonyl. And it's a carbamate protecting group. This is far and away the most common protecting group for amines. It's really, really reliable and really, really easy to take off. And the way we install it is we take our amino acid and it has that side chain coming off of it. And there's a variety of different reagents to put a Bach protecting group on. The one the book likes to use is this one. And this is called Bach anhydride. Or another way of describing it would be di. Oh, come on. My computer got hot. Just 1 second. Di tert-butyl dicarbonate. All right, so the reactivity is pretty straightforward. If we've got a amine and an anhydride, the amine can go attack our anhydride and kick it off as a leaving group. And when we do this, I don't know where my black marker went. Sorry guys, just 1 second. There we go. When we do this, we can install our Bach protecting group onto the nitrogen end, and it will exclusively protect the nitrogen. It won't touch the carboxylic acid alcohol, which is really nice. Oop. So the carboxylic acid end will just hang out on its own. And this entire functional group is oftentimes just referred to as Bach. People don't like drawing it out all the time. There's also another reagent used to install Bach protecting groups, and I really like it. It's labeled Bach-On. It always reminds me, do you guys remember the OxyClean commercials with the guy? Yeah. With OxyClean? I always think of him like selling it on an infomercial, like, get Bach-On for all your Bach protecting needs. There's a variety of different reagents, but that's my favorite one just because of the name. Bach anhydride is also very commonly used. The neat thing with this reaction is that it can be completely reversed. So when you don't want that amine protected anymore, you can react it with trifluoroacetic acid. And the mechanisms shown in your book, I'm not going to cover it, but the cool thing with this reaction is it expels isobutylene, which is a gas. So the reaction will start bubbling. As soon as it's done bubbling, you know all your Bach's removed. It's a really simple, easy workup, and you don't have to worry about purification. You just treat it with trifluoroacetic acid and then evaporate off the excess trifluoroacetic acid. Pretty cool reagent. All right, now let's look at our carboxylic acid protecting groups. All right, the way we protect carboxylic acids is very straightforward. We take our amino acid, we can react this with an acid source, and then react this with benzyl alcohol. What do you think happens when we do this? Yeah, just a esterification, right? So just like we did in our acetate esters lab, if you've got a carboxylic acid and an alcohol, you can turn it into an ester. Pretty easy. I'm not going to show the mechanism for any of that. But the nice thing with this ester in particular, what's that?
You swapped out the R with the amino.
Oh, thank you. I'm off today, guys. I'm off. All right. The nice thing with this specific ester is it's really easy to convert back. You can do hydrogenation. Actually, I'll label this as ORs. So hydrogenation works well. You could do HBr and acetic acid, which is actually the most common way of removing this. It's the easiest. Or you can react this with sodium hydroxide and water. So benzyl alcohol is really, really easy to deprotect when you're done with this synthesis. So first you protect your carboxylic acid, you do your peptide coupling, and then you can remove it when you're done. Okay, it's used for short peptide change. So in this case, I'm drawing it as racemic, but normally when you buy your amino acids, they're enantiopure, so I'm just not showing stereochemistry there. Yeah, that's a good question. All right, so this looks like a lot of work, and it is a lot of work, right? Every time you want to do a peptide coupling reaction, it's 3 steps, right? So let's think about this. So if we use this method, each peptide bond requires 3 steps. This becomes a problem for really long peptides. My favorite example of this is a drug called Fusion. Fusion is 38 amino acids long, 38 amino acids times 3 steps, talking about 114 reactions. You guys did 3 reactions, and I heard a lot of griping. Doing 148 reactions is hugely problematic. So Fusion, what it's used for is it's an entry inhibitor for HIV. If you're HIV positive and your drugs stop working, essentially this is a last resort drug. It costs over $30,000 a year to receive treatment because administering it's expensive and making it is crazy expensive. So long peptides are very, very problematic. So this is where problem 3 comes in. Problem number 3 was a big problem for a very long time. First problem was time. If we have to make a really long peptide sequence, it takes forever. Second one is cost. If we have to do 114 reactions to make one drug, that drug's going to be a really, really expensive drug. Third one is greenness. I don't know if greenness is actually a word, so I'll put it in quotes. But if we're putting on protecting groups and then just immediately removing them later, the atom economy for these reactions is just abysmal. You're wasting a ton of products, so the efficiency is basically in the toilet, and you're wasting a lot of your time and money. Chemists hated this for a really long time. So to kind of put this into perspective, I've got an example. Put into perspective. Fusion would take 114 reactions. Let's assume that we're really good chemists and we're getting 95% yields for each one of these reactions. What do you think the overall percent yield would be? Yeah, it's something that people don't really process, but the percent yield at the end would be 0.3%. Wow. So you'd have to start out with a metric ton of this stuff in order to get a dosage that would work for a group of patients. And so this was a very, very big problem. And so the last solution that we have I'm going to do this in red and give it multiple exclamation points, because this is really how chemists do it now. It's called solid phase peptide synthesis. So solid phase peptide synthesis is pretty unique. What you do, I had an image on here, but my computer doesn't want to pull it up. I'll show it to you guys tomorrow, but you can embed amino acids onto polymer beads and then link one peptide on, flush the polymer with the solvent, get rid of all your byproducts, do the next reaction, flush it, next reaction, flush it, and then it's actually completely automated now. So chemists oftentimes make fun of biochemists because they absolutely don't know the chemistry that's going on. They just type in a sequence, and then this machine just goes and spits out a product that's a certain peptide length. And so it's completely automated now. It's pretty cool. But even with that, it's still not green. And so there's an even better solution. So I'll do this in big red letters. Does anybody know what the even better solution is for making peptide drugs, or just peptides in general? I'll give you a hint. Living things are really good at making peptides. Yeah, we can program E. coli and yeast to spit out sequences of peptides now. So this is the next big thing in chemistry. And what this is called is directed evolution. So what directed evolution means is you can insert or mutate E. coli or yeast to make drugs, or molecules, I should say.
We know how to use your drug.
So this is a really interesting thing. I posted an article on the class website because there's a very large and growing group of biochemists out there that say organic chemistry is going to die. Pretty soon we won't need chemists. All we'll do is we'll plug something into yeast and yeast will spit it out, and then we'll just need chemical engineers to help clean it up. And so it's this big back and forth debate, and the article is really interesting. It actually has a synthetic chemist arguing against a biochemist and vice versa. Essentially, you guys can anticipate where I stand on the issue. I don't think organic chemistry will ever die. But I do think for large-scale production of drugs, we're going to see that being shifted over to E. coli and yeast. Do you guys remember that first molecule I showed you, first term Taxol, that big monstrosity where I said identify the functional groups? So that molecule is actually now mostly synthesized by yeast. It's a pretty incredible thing. It went from being a few month-long synthesis down to something that yeast can produce in a fermenter, or E. coli, I can't remember. So this is where chemistry is heading, but I think organic chemists will always have a place in that world. It's a really interesting read, though. One thing I will say is we are going to skip sections 25 through 28, but if you're taking biochemistry, I would really recommend reading through that. It'll provide you a lot of the foundations for biochemistry. It's just not really synthetically useful, and it won't be on the ACS. All right, so tomorrow we'll cover our lipid crash course. And then your problem of the day is related to peptide coupling reactions. It should be pretty straightforward, but let me know if you guys have questions.